Hello, everyone.
Hello.
Thank you very much for joining us online in person. And my name is Alvin Manpour, Director of the Steel Center. And I have the pleasure of introducing our lecturer today, Zaher Yousif. He's a seasoned structural engineer with 30 years of experience in bridge engineering. He specialized in highway bridge design, P3 project management, and a wide range of bridge types, including post-tension, precast concrete, and steel girder structures, as well as rehabilitation rating projects. So today's presentation focuses on a new bridge in Ontario, Gordie Howe International Bridge. And I'll let Zaher take over. Go ahead, please.
All right. Thank you. Thank you. Can you guys hear me clearly? Can you hear me?
I can hear you. Not
Yeah.
100% sure if the audience in the room can hear you. You have this. Is the speaker?
Okay, so Todd says it's fine where he is.
Can you say something, please?
Yeah. Gordie Howe.
Excellent. Yeah.
Okay.
Thank you very much. Go ahead.
Okay. All right. And you guys can see a screen. Hey, good afternoon, everyone. It's so I mentioned my name is Zaher Yousif. I am the Chief Bridge Engineer and Vice President Engineering with the Windsor-Detroit Bridge Authority. So hi, everyone. I think a few of you guys were on site and saw the bridge. Unfortunately, it was raining. We couldn't go to the deck, but today I will provide more detail about some of the interested item about the bridge and the project in general. So often we've been asked why we need the Gordie Howe Bridge, International Bridge crossing between Windsor and Detroit. If you guys, I don't know if you're familiar with the area. Currently in this area there is an existing bridge, almost 100-year-old, which carry the commercial and passenger vehicles, and we have the tunnel connecting both downtowns, Windsor and Detroit, but this tunnel carry only passenger vehicles, cannot carry the commercial vehicles. And this corridor is very important corridor for trade between US and Canada. Nearly $1 trillion worth of commercial crossing between US and Canada at this region. Almost 7,000 trucks cross every day on the existing bridge. Therefore, there was a requirement to have a second crossing to provide redundancy. The existing bridge it's a suspension bridge, was built in 1929. The improved border processing, our projects will have border processing facilities, which is a state-of-the-art. Capacity, our bridge, I'll provide more detail about that. The bridge will have more lanes, and also will provide highway-to-highway connectivity. So the bridge connect highway on the Canada side and US side directly without going through the internal roads, city roads in Windsor and Detroit. So the organization for our structures, we are the Windsor-Detroit Bridge Authority. We are the Crown Corporations. We report to Government of Canada through Ministry of Infrastructure and Community. We oversee by board of directors, and also we work with the international authorities. International authority is joint authority between Canada and US members. The international authorities task is to ensure compliance with the crossing agreement we have between Canada and US. And also we work closely with other partners on the Government of Canada, the Infrastructure Canada, and the Food of Canada Border Service Agency, MDOT, and then on the US side as well, Federal Highway Administration, MDOT, US Customs and Border Protection. On September 2018, WDBA awarded the contract to our private partner, Bridging North America, was selected as a successful proponents to design, build, finance, and operate the project. The operation of the project will be for 30 years. Bridging North America is comprised of a joint venture of contractors from Fluor, Dragados, and Aecon. Project location and overview. As I mentioned, the project located in Ontario, connecting Windsor and Ontario side and Detroit on the US side. There are 4 components for the project. The US port of entry on the Canadian side, and then the main bridge which is crossing the Detroit River, and the US port of entry, and then the connecting to Interstate 75 on Detroit side. These are the rendering for the 4 components of the project. On one, you can see the Gordie Howe International Bridge, is the cable stay bridge. And then we have the Canadian port of entry. When complete, that will be, these are rendering, and they are almost at this shape. At this stage, we are at 98% construction complete. And then the US port of entry, and then the Michigan interchange, the 4th components. The project, it's under the very sustainability and design feature is very important parts of the projects. So we utilize the LED lighting. The buildings are advantage of natural lights. The water management system was considered to reduce water demands, and also we added even to a stand of adding a Falcon box on our tower. That's part of the environmental requirements as well. So I will go through these 4 components of the projects briefly, and then I will focus more on the bridge, because you guys will be interested more on the steel for the building. The buildings, they are a 2-story, 3-story building, typical industrial building, and with the steel frame and in concrete and drywall, and typical that. We have the first one is the Canadian port of entry. The Canadian port of entry, it's approximately 130 acres in size, which include 130,000 square footage in building. Those are the building shown on the right side of the slides. We will have the 12th primary inspection lane. This is for the agency. This is for commercial vehicle, for the truck. And then we will have 12 primary inspection lane for the passenger and buses. If one of these vehicles need to go to the secondary inspection by the agency, so there are 35 secondary inspection bays for the passengers and bus, and there are 14 commercial secondary inspection bays in case of one of the truck need to go to secondary inspections. Of course, on site, who is going to be managing this one? It will be the Canadian Border Service Agency, and the Canadian Food and Inspection Agency will be the agency processing those commercial and passenger vehicles. The US port of entry, it's on the US side. It's larger than Canadian. The reason it's larger because every agency will have his own program as far as the size of the building, the number of the agency inspection, and the requirements for inspection as well. The US, it spanned over 167 acres actually, more than the Canadian was 130. So on the US also, they will have more inspection, primary inspections. We'll have 15 primary inspection for the commercial and 21 primary inspection lane for passenger. And if they will be diverted the commercial for secondary inspection, there we have 41 secondary inspection base for passenger dedicated as well for that. And the agency processing working on those building, they are the CBP, U.S. Food and Drug Administration, and U.S. Department of Agriculture, and U.S. Fishing and Wildlife Service. So those are the agency will be working to process the crossing people in the U.S. port of entry on the Detroit site. The Michigan interchange, this is the other components for Gordie Howe International Bridge. The Michigan interchange I-75 span over 1.8 mile roughly. This is the U.S. port of entry. So people leaving U.S. port of entry toward U.S., they will go through these connecting ramps. And the part of this project was building those connecting ramps to I-75. And also within the I-75, there were 4 highway bridges crossing I-75 were replaced with the new bridges, and 5 pedestrian bridges also, all pedestrian bridges were replaced with the new. In addition, all the utilities done across I-75, and I-75 was widened to accommodate the additional traffic coming and from Canada and moving to Canada. The bridge. So the Gordie Howe International Bridge is a cable stay bridge. Is designed for 125 years service life. The tower for the bridge, as you can see in this picture, the tower height is 722 feet of 122 meter tall. We have the bridge will be able to accommodate 3 lanes on each direction. So we have 3 Canada bound and 3 US bound, separated by center line here. The cable stay, the lane for each, is a typical lane for the bridge would be 3.75 meters, and the end of the cable stay on both sides, we call what we have the, you guys saw that, what we call them the approaches. These are typical steel girder bridges with the cast in place deck. And then I'll describe the cross section of the bridge and the type of steel used on the bridge. We will have in one side of the bridge, we will be able to accommodate the multi-use path, and also the bridge will be able to accommodate the oversized vehicle. And I will talk about some of the uniqueness about this bridge to accommodate live load compared to other bridges and highways we design in Canada and US. So the multi-use path is one side, so people will be able to walk and use and bike across the bridge in one side. The multi-use path is separated by concrete barrier from the traffic. The bridge is designed for 3 lanes in the initial stage in each direction, but it can accommodate the 4 lanes at the ultimate stage if needed in the future. If the traffic demand required increase the number of lanes, the bridge can accommodate 4 lanes in each direction by modifying some of the barrier location only, without adding anything to the main cross section of the bridge. The other advantage of this bridge, we will be able, is designed to accommodate oversized vehicle, as I mentioned, and also the hazmat material. Currently, there is a limitation on the type of hazmat materials can cross between Windsor and Detroit using the existing bridge. The superstructure for a bridge in this elevation, I don't know if the numbers are clear, but I will try to explain. I mentioned the total height of the tower is 722 feet. The main span, which is between the towers, is 853 meters. 850 meter span for cable stay This is making the longest cable stay bridge in span in North America. And the back spans, they are around 357 meters long. These are the back spans. The approaches on both sides, they will go beyond these points. The tower is constructed in land. This is the Detroit River. As you can see, the tower constructed in land. We did not want to interfere with the navigation in Detroit River. Therefore, the tower were constructed at the outside of the river. We allow for vertical clearance for the large ships to navigate through the Detroit River. It's a very busy river, actually. Large ships navigate daily through the river. Therefore, we maintain the navigation channel with a vertical height almost 46 meters, which allow any type of ship to cross under the bridge without impacting. The bridge was built in a way that will not impact anything in the as far as navigation in the Detroit River. The superstructure of the deck is built with a steel girders and floor beams. You can see on the top section here is more clear. We have the edge girder on both sides. And those two edge girder, they are 2.5 meter in depth, steel girder, connected by along the bridge with these blue floor beams. Those floor beams are spaced at 5 meters, roughly center to center, for the whole length of the bridge. And longitudinally, we have these beams. They are the redundancy girder going longitudinally to connect all the floor beam together. These are the main two girder at the edge, and the floor beam running transversely, and the bridge is designed as a box. So there is a soffit panel to close the at the end of this floor beam to make the box, to make the cross section of the bridge as a closed box. So basically, the purpose of that, we want all the utility to be inside the box. And then for maintenance purpose, anybody will be able to enter the box doing any work without having to put any netting or anything underneath. So there is a steel plate, make the bridge as a closed box. The deck of the bridge is precast, full depth precast post tension deck in two directions, transversely and longitudinally, with latex modified concrete as a wearing surface was 50 millimeter was placed on top. Tower and foundation. The tower type is what you call it inverted Y configuration tower. The tower leg will supported by two footing connected by tie beam. This tie beam is 1.5 meter deep, and there is a post tensioning going through the from one footing to other for the tower. 52 cables of post tensioning cable running in this direction to connect the two footing tower together. Each footing is supported by 6 3-meter concrete drill shaft pile. Those piles goes up to depth of 30 meters. And they are socketed in rock, around 6 meter socketed in rock. The design of the bridge. Another interesting aspect of this project is because it's international crossing between two countries, the requirement is need to comply with both standards, US and Canada. Therefore, the requirements from the designer was to do a dual design, they need to design for using the Canadian Highway Bridge Design Code S6, and also using the AASHTO LRFD code, which is used on the US side. Therefore, they will build two tracks. They call them Canadian track and US track. So the engineer of record was responsible to provide two sets of calculation, one using the Canadian code and one using the AASHTO code with different unit. As you guys know, in US, they use the US unit, and here with metric unit. But the final design drawing, they were produced in metric, and all the drawing on site or measurements were in metric. The construction of the bridge was using the Ontario's construction specification. In addition to that, we use those following standards were required for designer to provide in each Canadian track. For foundations, for durability, the FIB Bulletin 34 was used to maintain the service life to design the service life for 125 years. The live load study as a cable stay bridge is the longest cable stay in North America, and it's a signature bridge. The extensive live load study was done to investigate the type of loading in the region. In the left side, you can see these are data collected from the Michigan side. US use what you call it way in motion data. They monitor all the crossing in the region for the vehicle weight. And then using survey close to 700,000 vehicle, those are the number of truck in relation to the gross vehicle weight. And they will vary between, as you can see, between 100 kilonewtons up to 1200 kilonewton with the intensity of our. The reason we wanted to see what is the live load vehicle we need to design if we need to modify the live load from Canadian code or the AASHTO code. And on the right side, this is the data collected at the Ontario site. Ontario, they use what they call it the Ontario Commercial Vehicle Surveyor, CVS. They monitor the weight of, there are more than 20,000 records collected from Ontario on the live load study. In this study, they identify the intensity of the gross vehicle weight crossing in respect to number of truck. As you can see in Ontario, we are still within the 625 kilonewton, which is the live load used in the Highway Bridge Design Code, as you guys know. And that was the, so at the end of the live load study, it was determined that the Canadian track design code, the CL 625, Ontario, it stay as it is in the design code. But the US track design code, because US use what we call HL93, which is around 300 kilonewton with 3 axle load. We found that because of the study I mentioned and the surveyor mentioned in the previous slide, it was found that we needed to modify the AASHTO track used in the design. So we created a new track called WDBA AASHTO track load, which increased the load to 440 kilonewton and increased number of axles to 5 instead of 3 for HL93, the typical track used in AASHTO design. And in addition to that, it was investigated that we wanted our bridge to be flexible for moving, and I will talk about the ITS, exchanging the number of lane between US and Canada in case there is a additional load, heavy traffic toward Canada. We can increase number of lane to become 4 lane toward Canada, 2 lane to US. So therefore, we design all the lane to be as what we call it mixed lane. Mixed lane is meaning commercial and passenger vehicle. In addition to that, it was considered the lane load as because of long span bridges. You need to consider the loaded length together with the live loads. It's a signature bridge, cable stay, long span. Therefore, we need to consider all the other design loads in the code. So we allow for additional utility in case there will be future utility need to cross between Windsor and Detroit. We allow for design, what we call it, the marathon. There is a few days during the year. There is a marathon running between Detroit and Windsor using the bridge. So the bridge will be closed for traffic, and there will be a marathon cross. So we wanted that to be considered in the design, and of course the thermal gradient loading was considered. The bridge was considered a lifeline, irregular critical structure. This is a requirement for seismic design. Those terms, lifeline, regular, critical structure, is the same, but because it's the AASHTO, they use different terms than the Canadian code term. But I added all the terms here. Even we didn't have any infrastructure in Detroit River. We wanted the foundation, they are close to the river, but they're not in the river. We wanted the embankments, the seawall on both sides, which separating the foundation from the river, to allow for designing of the vessel collision load with the criteria shown here in this one. And of course, we allow for snow load as well. To keep or to achieve the service life in the bridge, 125 years, we have we had some special design requirements as far as the material. So the reinforcement steel in the deck, in the precast deck, for both the approaches and the main bridge is all stainless steel. There is no black steel, all galvanized used on the bridge, stainless steel. The concrete is high performance concrete. The structural steel specify it's as you can see here. We give few options for the steel, the ASTM or the 250 and then 50, depending on which element of the bridge. And the requirements to keep the durability and service life, where all the steel will be coated. And even if they use a weathering steel in some area, the weathering steel were coated as well. And the grade of reinforcement is shown. We allow them to provide alternative for fiber reinforcement polymer, but it's used in some small miscellaneous elements, not the main bridge. The stay cable, the number of cable we have in the bridge is 216 cables. Those cables, they vary as far as number of strands inside each cable. Their number vary depending on the length of the cable, starting from shorter to longer. So in some cables, we have 38 strands. In some of the longest cable, we have 121 strands within one cable. And these are typical post-tensioning strands used in the post-tensioning bridges, which they are grade 270. The cable itself, because this is to maintain it was designed for service life of 100 years. Therefore, it's being protected. The strands are protected by sheathing for durability purpose. In addition to strand is protected, there is HDPE pipe on top around that also as well. This is just one of the nonlinear analysis for this is only the edge girder. The result of nonlinear analysis for the girder, just to show how they wanted to do that to see where longitudinal post tensioning in the deck will be added. One thing I forget to mention, the reason why we had the precast deck panel post tensioning in both directions, one of the requirements as well were we wanted a zero tension in the deck under the service load. So therefore, they need to have those transverse post tensioning and longer post tensioning in the deck. We didn't want it to go through rehabilitation and maintenance and to keep the longer service life for the deck. As far as the durability started actually from it was in the design, in the construction and operation. In the design, we specify the material, as we mentioned, the superior material, stainless steel, concrete cover, and the mixed design, superior mixed design, need to be considered to in the design to achieve the durability requirements. In the construction, we identify some of the means and methods which will enhance the durability. The materials selected during construction need to be selected in a way to achieve the durability as well. And of course, during operation, we will continue doing the inspection, typical inspection and rehabilitation work to maintain or achieve the service life and also the residual life at the handback after the 30 years. For this kind of bridges, as you guys know, it's the wind testing or the design analysis for winds. You cannot always use the code. You require the wind tunneling testing. The test was done at RWDI. This is one of the largest wind tunneling testing in North America, actually. It's here in the Gulf, Ontario. So we did the modeling test, wind tunnel testing at that area. The test was done for multiple stages, and the intent of the test that we wanted the bridge will be stable at all stages for a time period of 1,000 years. If you interpret that, you are talking about around 442 meters per second wind, and in the final stage will be in 10,000-year return period, which is goes up to 172 kilometers per hour. So the first test on the wind tunnel test was the cross section itself, and we wanted to test this for static drag, flattering stability, vortex shedding, and buffeting. These are the requirements for wind tunnel tests. You want to test the cross section for it. This test was done for up to 156 miles per hour test actually, and shows a good stability. I witnessed this test myself, so it was quite stiff in cross section, let's call it. And then the full aeroelastic model, the complete bridge model was built and was tested in multiple stages during construction. And I'm going to show you guys how this bridge was constructed. The tunnel test was done for every segment before completing until reach to the final, what you can see here. And the final test for was modeled at the wind tunnel. It's the tower itself. This is a freestanding tower was tested. The reason why, because you will build the tower before you put the deck, before you have the cable. So basically the tower works as a freestanding. Therefore, we want it during construction. Before you start supporting the tower with a cable on both sides, the tower will behave as a freestanding column. So it was tested at the wind tunnel for that behavior as well. The wearing surface we use for the bridge is latex modified concrete. They have two options, either using waterproofing membrane and then asphaltic concrete. I think similar to the system in Alberta, what I used to do there when I specify when I was there, it's similar, but the contractor elected to use the latex modified concrete, which is a special mix of concretes. It'll perform very well actually with a service life. It's up to 40 years. So that's in general the design. So the rest of the slides, I don't know from the time how we're doing. So I have another probably 8 or 10 slides shows the construction. I will just go through them quickly, and then I will open for a question after that. So this is some pictures about the foundation. As I mentioned, for the tower, there were 3-meter diameter foundation drill shafts. It goes up to 30-meter deep. Those foundations, their factor ultimate compressive load was up to 17,000 tons. So it's, as you can see, it's quite significant load coming from the tower and from the deck. This is the during construction of the tower. This is the tie beam I mentioned connecting the two foundation. It's connected by post tensioning cable running in this direction, 52 post tensioning cable. The tower was constructed with the jump form on both sides, the US and Canada, with multiple steps of this, with the concreting, using concrete inside. The tower it's a voided tower, is a box with elevator running through the tower. In the final stage, we will have 2 elevators running to the connection here, and after that we'll have 1 elevator running to the top. So that's the method of, I will show more detail, but that's the way it was constructed. You can see when the tower reached to this certain height, they start erecting the deck and connecting the cable to the tower. So that's the method used for erecting of the deck. Typically, those kind of bridges, sometimes they've been erected from the barge in the river, and then they lift the piece one by one to the bridge from the river to the deck. What the contractor selected for this to avoid impacting on the navigation of the river, they completed the backspan on both sides, and they erect the backspan on temporary supports, and then they will start mobilizing the equipments from the elements for the bridge from this side, and then they put a crane, as you can see the crane here at this side. So the all the member will come by the truck from the land and then erect piece by piece. As soon as it's complete, place the deck, do the stitching part between the deck, and then connect the cable and move to the next piece. And that's the way where the bridge was constructed, without any impact on the navigation channel. These are the side span, as I mentioned. They are typical steel girder bridges. This is the cable stay bridge. It's a closed box, but these are the approaches, which they are typical steel girder bridges. We have 9 span in each direction. And this is more pictures about the approaches. It's a curved steel girder bridges with the diaphragm. This shows the approaches when they cast the deck after that. So the cable stay ended here. There is expansion joint at this location. At the tower location, how the cable is connected, I think this is maybe you guys would be interested. Inside the tower, there is this huge steel box, empty steel box with all these shear stud, and then and the jump form will come on that, and then there will be concrete surrounding that. So inside the tower, it will be this huge steel box will be placed. And the anchorage, you can see this opening here, and the cables will run from here through the steel box here. This is a concrete outside face, and this is the cable running to the deck, and the strand will be driven to here, and that's the dead end of the cable for the anchorage of the cable for stressing. This is some more picture. Of course, the tower, there was a tower crane connected to the tower during construction. It was needed. This is the final step when we reach to connecting the US and Canada side. You can see the crane. So this is the actual picture. So the bridge was reaching for, the construction was coming from both sides, Canada and US, until they reached to the center, almost the center location. And then the frame was connected between the two segments. And it was very smooth connection. We didn't have any survey or any issues on the connection. So the two crane on the Canada and US side connected the two sections of the placed the precast deck panel. That was one of the very great milestone achieved by, as soon as you connect it, now it's become a border crossing for that. This is how the cable, I mentioned about the number of cable we have. This is how the cable is connected. That's the steel things coming from the tower. And then they start threading this strand one by one through the HDPE pipe. Those HDPE pipe, they vary in diameter, depending on the number of strands inside them, from 38 to 121, 22. And that's the final. There is a small short video for that if you guys are interested, but I think you can see it at the website. You can allow some time for questions if you guys have.